Hello everybody, my name is Timothy Guter and I am glad to show you our presentation, which we completed in collaboration with Ilya Zisman and Denis Rashipkin, my course mates, on behalf of Higher School of Economics, Moscow, 2018. So, the disjoint union set is a really interesting data structure. For what purpose should we use this data structure? For instance, do you know about Cruscal algorithm? If you don't know, don't worry, it's okay. So, the purpose of this algorithm is to find the weight of the minimal spanning tree of the given graph. So, given a graph with m edges and n vertices, each edge has its own weight. So, and we should just construct minimal spanning tree. So, the spanning tree that has minimal weight. Okay, step 1, sorting all edges in ascending order, but by its weight. The asymptotic of usual sort is m multiplied by logarithm of m. It's usual approach. So then let's start looking on the edges from minimal weight, of course, and add edges to the spanning tree if and only if current edge connects two different connected components. So the main purpose is to find how to find if two different vertices that are connected with one edge lies in two different connected components. So the straightforward approach use linear time. So it's just this approach needs just to go through all the vertices and look at the number of connected components that vertex has. So let me introduce disjoint union set. First of all, this data structure helps us implement following operations. Check if two vertices lies in one connected component or not, and connect two components like at the edge in Cruscal algorithm. So asymptotic of straightforward approach, just linear. If we use some heuristics like path compression heuristic or range heuristic, this asymptotic will be just log n. And if we use both heuristic, the asymptotic will be even just O of 1. So, okay, let me just show you the basic version of our disjoint union set. Here is, you can see the program, which supports three operations. First operation is add. It's just add new vertex to our graph. The second operation is connect. This operation connects two vertices, one and the first and second. So, and the third operation is show. This operation provides us information about to what connect components belongs each just vertex. So, how we implement make set? It's like basic operation. We just append our vertex to the end of our list called DSU, disjoint union set. So, find set. This operation, first of all, this operation just checks if our vertex is the parent, the main vertex of its tree. It's connected like tree, and if so, just return this vertex itself. If it cannot be returned, so if this condition like doesn't follow, we just find the parent of such vertex by implementing recursion algorithm and return it. And the third operation, union sets, just use this operation uses operation find set, find the parent, the main parent of each vertex, and just I don't know, just look at all at parents of first vertex and parent of the second vertex, and add full tree of first vertex to the tree of the second one. So let me just show you some example how does it work. So first of all, let me add 6 vertices from 0 to 5. Okay, then let me just connect maybe vertices 0 and 1. Oh, I'm sorry, it's just a mistake. Connect with double N, of course. Let me just repeat. Yes, sets are joined. And maybe 2 and 3. And then I want to connect vertices maybe 0 and 2, so make a full connected component. And please show me the result. So the parent of 0 vertex is 1. This one, of course, it's true. The parent of the first vertex is 3. Of course, it's true. And the parent of 3 vertex also, this vertex itself. So, and about vertex with number. Oh no, of course no. It's the parent for second vertex, because we enumerate our components from 0. So the parent of the second vertex is 3, and the parent of the third vertex is 3 itself. And the vertices 4 and 5 just remain, I don't know, disjoint, because so we didn't use some operations about it. So it works, yes, but it works, of course, really long. And first approach to make our program just more faster is heuristic of path compression. So just look at the picture and see. Oh, I'm sorry, just a mistake. Okay, let's see. What if we will just reuse our operation of find set operation, and after implementing find set operation by the vertex number 5, our tree will be like this. Now we don't we don't relocate we don't appoint the new parents of our vertex. So this our tree will be remain as it was. But after this heuristic of path compression, for each vertex 2, 3, 4, 5, its parent will be 1. Of course, in the next step, if we just want to find the parent of for example vertex 4, it will be done just by one operation, because the parent of vertex 4 will be the first vertex. So but if we don't do that, it will be 1, 2, 3 operations. So this approach can be shorten our time. How to do it? So now we find the main parent of our vertex. Let's just appoint it to our DSU array and make it equal to p. So this just one line makes our program works with logarithmic asymptotic. So, but there is a second approach, range heuristic. What if we have just 2 separate trees, 2 separate components, and want to make it to gather it to make the one. Is it a good idea to connect the tree with more vertices to the tree with less vertices? Of course, it is not a good idea, because after it we must go through the our vertices to reach the last destination. Of course, the best idea will be connect the tree with less number of vertices to the tree with more number of vertices. Okay, just let me just realize it. We should first of all, we should create a new array called rank, because its array will be consisted of the number of vertices if vertex sub 3. So just number of vertices. Okay, so let me add some line to the make set procedure. First of all, we should appoint rank, append the one to our rank array. Why? Because firstly, our vertex consists only of one vertex itself, because it's rank. We can just I don't know, consider it like a size, rank, size, something like this. Okay, so, and in union sets, when we just found, if we just found the two parents of two vertices, we should just check what vertices should we add to what. So now we add sub 3 of vertex A to sub 3 of vertex B. So it may be not a good approach. Let's just check if rank of vertex maybe B. So if rank of vertex B less than rank of vertex A, then we should appoint appoint B to A. So what can we do with it? Let me just make this approach. dcu at B is equal to A. If it doesn't implement, just appoint to A vertex, B vertex. So almost all, but also we should of course recalculate our rank of our vertex. Okay, how can we do it? Okay, just in this line and in the second condition we should add to y size rank of B, just rank of A plus or equal rank of A. In this case, vice versa, we should add to the rank of A rank of B. Okay, let me just show you that it works. It works just almost in the same way. Let's add 6 vertices. Add the second one, third one, add fourth one, add fifth one. Okay, let's connect separate first 3 and the second 3 vertices. Connect 0, 1. Connect, let me just connect 0, 2. Connect third 4. Connect third 5. And connect 0 and third. Maybe like this. So, show. Okay, so now you see that all our vertices belong to the one subtree. So the zero vertex and the first vertex to the second, and all following vertices to the fifth vertex. And why, for instance, first two vertices like don't belong to the fifth? Because we didn't use the function that that could add these two vertices to the fifth. But as you see, the last four vertices have been added to the last vertex. That's these two heuristics work in like a constant. Asymptotic is constant. So if you want to use disjoint union set, if you want to create a spanning tree, just use these two heuristics and it brings you like fast and reliable program. So thank you very much for your attention. That's it, and maybe we will create new relevant and good videos. So please leave your comments and like have good time. Thank you. Bye.